Hello and welcome to this lecture series on finite field for error control coding. My name is Sumit Kumar Chaube and today we are going to discuss about binary field. Okay, but before we discuss binary field, let's quickly review some of the concepts that we have learned, or basically the definition of the field. Okay, a field is basically a triplet, a set together with two operation addition and multiplication if and only if it is satisfying certain conditions, and the very first of those conditions is that multiplication has to be distributive over addition. What that means is that for all ABC element of F, A times B plus C should be equal to A times B plus A times C. Apart from this condition, this set F under multiplication should be a commutative group. So it must satisfy closure, associative law, identity inverse, as well as commutativity. Now non-zero element of this set F under multiplication should also form a commutative group. So it should satisfy non-zero element of the set F should satisfy closure, associative law, identity inverse and commutativity under multiplication. Some of the fact about this field is that order of the field is the number of element of the field, and a field with finite order is called finite field. So a field in which there is only two elements is going to be called binary field. So let's start with binary field arithmetic, but before that we are going to define our binary field. So in our binary field, the set contains only two elements 0 and 1, and the addition is modulo 2 addition. Similarly, multiplication is modulo 2 multiplication. Here is the Cayley table for multiplication. From this Cayley table, it is clearly visible that it is closed under addition, modulo 2 addition. It is associative, it is commutative. Identity element is 0, so 0 is our identity element here, and 1 is additive inverse of 1, 0 is additive inverse of 0. Okay, and as well as it is going to be commutative because you can see that along this principal diagonal it is symmetric. So this is a binary additive group. Okay, now we will see this multiplication sign. Now you can see that we are going to consider only non-zero element. So in non-zero element I have only one element. Okay, and no matter what you do with this, it's going to remain 1. So again it is going to be a commutative group. It's a very trivial group, but it's a commutative group under multiplication. So we can say for certainty that this is a field and this is a binary field which contains two elements. Now why do we consider binary field? Because it plays a very important role in coding theory. It is widely used in digital computers and digital data transmission or storage system. The reason behind that is that our digital logic has two labels. So digital logic has two labels, high and low, and here again we have only two elements 0 and 1. So binary field and its extension are used for coding theory and in general digital computers and digital data transmission. Now we are going to start with binary field arithmetic, but before that we have to quickly define some of the things. So the very first thing is that polynomial. So a polynomial over GF2 has a general form of this, that it is going to have a general form like this. What I mean by that is that the coefficient of this polynomial should be in GF2, should be element of GF2. So the field will be something like, and they can be only 0 and 1. So we can have a polynomial like this: x square plus 1, x plus 1, x square, okay, and x cube plus x plus 1. So these are the example of polynomials over GF2. Okay, and their addition is defined in this way, that when we add two polynomials, we are basically adding them together with their coefficient by modulo 2. So we are doing the coefficient by modulo 2. Okay, so if we have x plus 1 and we are adding this to x square plus x plus 1, our result is going to be x square plus 1 plus 1. This is again modulo 1 addition, modulo 2 addition, 1 plus 1 x plus 1 plus 1. So you will see that this is going to be 0, this is going to be 0. So our result becomes x square only. So this is how these polynomials are added together in this binary field arithmetic. Now the multiplication is done in the similar way, and we are going to do the coefficient by modulo 2 there as well. Whenever if a polynomial is multiplied with 0 element, that is 0, result is always 0. So these are the three things that one has to keep in mind when working with the polynomials in binary field. Okay, now we have a definition of irreducible polynomial. If fx is a polynomial, is said to be irreducible if it is not divisible by any polynomial over gf2 of degree less than n but greater than 0. Let's say the degree of fx is n, then it is said to be irreducible if it is not divisible by any polynomial over gf2 of degree less than n but greater than 0. So one of the example of these kind of polynomial is x plus 1. It's a polynomial which is not divisible by this degree 1 polynomial, which is irreducible. Another example here is x square plus x plus 1. So these two are our irreducible polynomial. But if you consider this x square plus x, then actually this polynomial is factorized. So this can be written like this: x times x plus 1, and you see that clearly it is divisible by x or x plus 1. So that's why this is a polynomial which is not an irreducible polynomial. So this is not an irreducible polynomial. Okay. Now we have a theorem over irreducible polynomial, which it's much easier to prove once we learn how to construct an extensor field, but nonetheless we are going to discuss it right here. So any irreducible polynomial over gf2 of degree m divides x2 to the power m minus 1 plus 1. So for example, x square plus x plus 1 is an irreducible polynomial of degree 2. So degree of this polynomial is 2. Then it must divide x to the power 2 to the power 2 minus 1. So 2 to the power 2 minus 1 plus 1. So this actually divides x cube plus 1, and which is much easier to prove. You can see it here, right here, that x cube plus 1 when divided by x square plus x plus 1, we can multiply it by 1. So you will have here x cube plus x square plus x, and the remainder will be here in this case x square plus x plus 1, and then it is 1, and then you will have x square plus x plus 1, and you see that this is all cancelled, so remainder becomes 0. So in that sense it is actually dividing this x cube plus 1. Similarly, an irreducible polynomial of degree 3, x cube plus x plus 1, will divide x2 to the power 3, which is equal to 8 minus 1, so 7 plus 1. So this must divide this, and this is a homework. You can verify that it is actually dividing. Okay, so this is one of the theorem, and it is a very important theorem, that any irreducible polynomial over gf2 of degree m divides x2 to the power m minus 1 plus 1. Okay, we will prove this a bit later. Now there is another definition of a primitive polynomial. So a primitive polynomial is one which is basically a irreducible polynomial px. Okay, so an irreducible polynomial px of degree m is said to be primitive if the smallest positive integer n for which px divide x to the power n plus 1 is n is equal to 2 to the power m minus 1, and we have already seen that any irreducible polynomial is always of degree m should divide x to the power 2 to the power m minus 1 plus 1. Okay, so other than this polynomial, it should not divide any polynomial of degree less than 2 to the power m minus 1. Then this polynomial is going to be called primitive polynomial. So example of primitive polynomial here is x to the power 4 plus x plus 1. This divides x to the power 15 plus 1. Okay, and it doesn't divide any other polynomial of degree less than that. So it divides this, but it doesn't divide x to the power 14 plus 1. It doesn't divide it. X to the power 13 plus 1. It doesn't divide it. So on and so forth. Okay. Another example here. This is actually a counter example. x4 plus x cube plus x square plus x plus 1 is an irreducible polynomial, but it is not a primitive polynomial. Why? Because it divides x to the power 5 plus 1. Okay, so this is about primitive polynomial, and we will see the list of primitive polynomial at the end of this lecture, but you should know this. Now we have something of a information about irreducible polynomial, that for any m greater than 1 there exists an irreducible polynomial of degree m. The same thing is for primitive polynomial as well, and in general irreducible polynomial and primitive polynomial for degree m can be more than 1. So there can be two primitive polynomial of degree 5 or 6, something like that. Okay. Next, we have a very important theorem that for L greater than equal to 0, f of x to the power 2L means if we have f of x, which is a polynomial over binary field, then this to the power 2 is actually equal to f of x square. Similarly, f of x to the power 4 is actually equal to f of x to the power 4. F of x to the power 8 is actually equal to f of x 8. Okay, and if we use this, it becomes very easy to do the manipulation over binary field. So we are going to first prove it, and then we will use it in the coming session. Okay, so let's say that our f of x is defined like this. So f of x is actually equal to f0 plus f1 x plus f2 x square plus f2 f3 x cube, and so on all the way up to f of n x of n. So this is a polynomial over gf2 of degree n. Okay, so when we square this, so if we square this, we are basically squaring right hand side as well. So we are going to square this as well. So if we square this, I can expand it a, and we can consider this term as b, and it can be written as a square plus b square plus 2ab. Okay, so this will be f0 square, okay, plus f1x plus f2x square dot 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 fn x to the power n whole square plus 2 times f0 and the same, let me call this this b, so this is f0 b. Okay, now what is 2? 2 is anything which is greater than 1 has to be converted back to modulo 2 format. So if you divide 2 by 2, the remainder will be 0. So this 2 becomes actually 0, isn't it? So since it is 0, since it is 0, we can rule these things out. So this square simply becomes this, and in similar manner we can expand it. So if we expand it along the same line, our answer is going to be f0 square plus f1x whole square plus f2x square whole square, so on and so forth. So you see that f1 square, f1 can be either 0 or 1, f0 can be either 0 and 1, and there 0 square is 0, 1 square is 1. So this is going to be f0, this is going to be f1 x square, this is going to be f2 x to the power 4 all the way up to f of n x to the power 2n. So this is basically equal to f of 2 of x, sorry, so this is actually equal to f of x square. So we have proved that f of x square is actually equal to f of 2 square. So this, we started with f of x whole square and we got answer as f of x whole square. Okay, so this is a very important definition, a very important result here in binary field, and we use it very often. For example, if I have to, let's say, multiply x cube plus x plus 1 with x plus 1, I am multiplying these two, x cube plus x plus 1 with x plus 1. So I can simply write it that x cube times x plus 1, and then we have x plus 1 whole square, isn't it? So we already know what is this going to be. This is going to be, according to our result, this is going to be x square plus 1, and this can be easily done x to the power 4 plus x cube. So in this manner it is very useful. Let's say you have to simply square x cube plus x plus 1 and we have to simply square it, then this will be equal to x to the power 6 plus x square plus 1. So it's very easy to do this. If we know this result, then manipulation becomes very easy. Next, here we have a list of primitive polynomial over GF2, and we generally require in our manipulation only of degree 3 and degree 4. So this is all that you have to remember. But anyway, primitive polynomial of degree 1 is x plus 1. Primitive polynomial of degree 2 is x square plus x plus 1. Primitive polynomial of degree 3 is x cube plus x plus 1 and x cube plus x square plus 1. Primitive polynomial of degree 4 is x to the power 4 plus x plus 1 and x to the power 4 plus x cube plus 1. From degree 5 onwards, we have quite a few primitive polynomial, and we don't really need primitive polynomial degree 5 in general. So this is all that you have to remember, or you have to understand, and you have to actually, it's a very good exercise to prove that whether these are primitive polynomial or not. And you already know the definition of primitive polynomial, so it is very easy to actually it's a little bit tedious, means you have to divide all those with all those polynomials, but it's a very good exercise, and it will also get you started in manipulation of polynomials, division, addition and multiplication over GF2. So for this reason it is very important. So this is an exercise, this is going to be homework to prove that all these polynomials from degree 1 to 4, I'm not going to give you degree 5, are indeed primitive polynomials. So those which are given here are indeed primitive polynomial. It's going to be your homework. So this is your homework. Thank you. I will see you in the next lecture.